Okay, in this video we're going to take a look at manual calibration of models. And basically what we're trying to do here is get the groundwater model to have the same behavior as some kind of real system, a real alluvial aquifer, say. And the way we'll do this is take some observations that we're using to characterize the real system, and then adjust some of the parameters in our model so that our model behaves in the same way that the observed, or that basically so our model matches the observations. So typically what we're going to do if we have a model that looks like this, our idealized alluvial aquifer, is have observations that consist of hydraulic head measurements at monitoring wells. Here these 5 monitoring wells as an example, and often they'll occur in they'll be stored in a table here, so each row is the value at a certain well at a particular time. And so those are one set of observations of hydraulic heads. And then we also might have some other kinds of observations, and one commonly used one is the base flow at a gauging station. So if this is a stream here, you can imagine that we've got a gauging station that measures the flow at this point, and the average base flow at that point is this value. So that's another kind of observation. And then to calibrate the model, what we would do is we would estimate values of K and R that the best match, they allow the model to give values that best match these observations. Okay, so that's going to be the general approach. And for this example, we'll depart from our previous cases and use anisotropic conditions where the K in a horizontal direction is 10 times greater than K in vertical. This is typical to have this kind of anisotropy in bedded sedimentary aquifers, and the way that you'll do that is by using this VANI file in ModFlow, and the value will be the ratio of horizontal K to vertical K. Here's the URL if you want to go and learn more about these particular files in ModFlow. So let's go over to GMS, and here's the model. And this is a model that'll be fairly well calibrated. These are the points in the model, the observation points of heads, and then this little symbol gives us a graphical depiction of how good we're doing with the calibration. And because this bar is going down, that means that the calculated value from the model is less than the observed value, but because it's green and not yellow or red, that means that even though it's low, it's pretty close. So that's what we'll be shooting for. And let's just go and start from scratch and build this model up from scratch. And I know that you've done this before, but we'll just go ahead and start with a base map and run through this just for practice. So we can start with the base map, and then we'll register the image using these points and put them here in the corners. This is a map very similar to what we've had before, but it will be it has this come on. Oh, there we go. Y is 2000, X is 0, X is 0, Y is 0, X is 7000, Y is 0. Okay. So there's our registered map, and let's add in a conceptual model. And this is problem number 3. So we'll start first with the boundary coverage. And that will be, we'll have 5 layers for this model. And used to define that, yep. Okay. And then we'll draw a line around the region and make this into a polygon. And that will be the baseline coverage that we'll use. So we'll build that polygon. And there's the coverage for the boundary. And if we copy that or duplicate it, then we'll make this coverage be the conductivity and the recharge. And so coverage setup would be recharge, horizontal K, and horizontal and vertical anisotropy. So that looks good. And now we'll put in a new coverage. I'm not going to copy this one because this is going to be the stream. And it'll be a different shape. So we'll click that guy. Stream will just be in the upper layer. That looks like a good setup for the stream. The spelling looks like it's not, like it's perhaps a little bit creative, but that's okay. And so we'll draw this guy in, put the stream in here, and we'll put another stream in down along this side. And let's see, we'll set up then the attributes. Well, the thing for the attributes that we want to do for the stream is go to select arc, click on the arc, and make it a specified head type. That's what we'll need for that guy, and we'll also need to do that here at the end. Specified head. And now to set the attributes, we just click on the node, and we make that node equal to 10. And these guys are, check it, but the default is that it's equal to 0, which is what we want all 3 of these nodes to be. So we're good for setting up the stream. And now we select the attribute table for the conductivities and recharge. And we'll just use default values here. So we've been using 10 to the minus 8 for meters per second for the recharge, and the conductivity, horizontal K of 10 to the minus 4, horizontal anisotropy would be 1, and vertical anisotropy, remember the ratio of KH to KV, and we'll give that as 10. Okay, so that's the setup of the map, and now we need to add to this grid frame. So there's the outline, and then we go map to a 3D grid, and we'll use origin and length that we've set, and the number of cells in the x direction is 140, the number of cells in the y directions will be 40, and we'll have, we'll say it's 20 meters deep, and it's 20 meters high, and there are 5 layers. So that should generate the grid. Yeah, that looks good. And now we just need to go up here to the grid and add a mod flow model to it. And we've got this baseline model set up here with the map data. We write it over here to the mod flow files, and then we should be able to run it. So, I'm going to give this a name. So 3_1_v1. Okay, so there are the results, and let's just do what we've done in the past and turn off the cell edges. And if we select head here and go into display contour options, we can go to this color fill and linear that gives us a little bit of a nicer output. Okay, so that's very much like what we've done in the past. This is really just our starting point. Now, we want to go in and put in these water level elevations that we were trying to hit during the calibration process. And so to do that, we go back here, left click on problem 3 to select it, and then right click to add a new coverage. And the new coverage we'll call observation wells. And we'll click over here, observation points, hydraulic head. And they'll be in layer 1, which is what we want. Alright, so now we've got to put these guys in. And the best way to do that is to turn off this the output from the model. Now we can see the underlying base map. And if we click here, points, we can select these points and just go and put them right on in there. Okay, so now we've located them and we've set up the coverage, and now we need to set up the attributes. So the best way to do that is to go up here to select point and select A. And what we'll do is just go through and enter the correct name for these points. Okay, so now we've got them all named properly, and now we can go in here and select this guy again. And here we got show selected. Well, if we show all of them, then show all of them. Okay. Well, we need to show all, and then the BC type any none. What I did was when I selected A, when I named A, I changed the type to observation points, but I didn't do that for the rest of them, so they didn't show up right away. But now they do, and I'm going to go and change the type to these observation points. It's just easier to do it all at once here. Okay, so now all our points are in, they're labeled, and we can go and put in the values of these observations. And to do that, let's just see if we can bring up the PowerPoint. And let's see, there it is. And so there are our values. And we just type it in there. See it at the same time. So let's see if I can do that. some reason it didn't. That's odd. What it's doing is okay. There we go. That seems to be working all right now. So there are the points. They're all labeled as observation points, and I'm going to put in these values. And I need to move that down just a little bit. Now I go here, and I can just go and type them in. So the observed head is 27.2, and we just put in these values. Okay, now, you see also in this column it's the observation head interval. And what's going on here is that this value here, 27.2, we put it in as a single value, but actually the water level in this measurement has some uncertainty associated with it. The water level in wells actually changes with time. And so if we were to make many measurements of the head, they would be different, and there would be some distribution. There also may be some uncertainty just in the measurement of the datum. And so we can put in the uncertainty in this measurement here by this is the interval, and this is 95% confidence. And so if we enter that and the interval, this would be 1 meter, plus or minus 1 meter is a 95% confidence interval, and then that gives us the standard deviation it calculates it automatically. And so we'll just use the defaults for now, but in a real field application, we probably would have some data where we could enter this ourselves based on our data. But this will be sufficient for now, so we'll hit OK. And now we see that now that we have these observation points, we get this bar here, and the lines from there down to there are defined by the uncertainty interval, the confidence interval, and we see that our calculated value is less than our observed value. And because it's red, that means it's a good bit less. It's less than 2 95% confidence intervals. Okay, so that is pretty good setup. So what I'm going to do is just recalculate everything and see where we are. So we have these results, and well, here, before we go to there, if I just click on this point here, I see down in the corner that my computed value at this point A is 19.5, and the observed is 27.2, so we're low, and we're low by 7.6 meters. Okay, so that's the result for that point, and if we click for that for the table, we see here all of the computed values and all of the residuals. Okay, so what we want to do now is take this baseline model, and we want to adjust the parameters, and we can adjust either K or R or both in order to try to make this match better. And so the way we'll do it is we'll fix the value of recharge, and we'll adjust the value of the conductivity to try to improve the match. Okay, so the way we'll do that is by copying these residuals and then going over here to Excel and pasting the values. So these are the residuals for the different points. And what I'm going to do is add them up. So that's the sum of the residuals. And we don't do squared for now because we want to have the sign. We want to know whether it's positive or negative. And then up here, I'm going to keep track of the value of the recharge and the value of K. Okay, so there's our data, and that value there is characterizing how well we're doing. So we have a sum total residual of 18, and the computed values are less than the observed values. So what that means is that we're off by a bit more than we would like, and so we want to try adjusting K and see if we can improve that. So because our computed values are less than our observed values, if we reduce the K, if we make the formation tighter, then that's going to steepen the gradients for the same amount of recharge. If we steepen the gradients, we'll increase the head. Okay? So because our values are all too low, we know that the conductivity is too high. So what we'll do is reduce K, and I'm going to just go in here. Really don't know too much about the system just yet, so what we're going to do is just basically guess, and we'll do, let's reduce K by a factor of 10, see what that does. So 10 to the minus 5, and hit OK, and then just write that over into the modflow files, run it again, and after we're done running it, we'll get the residuals for that run. So go to the observation wells, click on this guy, attribute table, and take a look at all of them. And here they are. Wow, some big negative numbers now. So what I'm going to do is, I'm really just wanting to deal at this point with the sum. So I'm going to paste this guy here. And there's the sum, all of the residuals added together. And I keep track of this. So, okay. Okay, so here's what we got. When K is 10 to the minus 4, we have a residual of that. When K is 10 to the minus 5, we have a residual of that. So we're positive here and real negative there. So the good news is that K is, we've bracketed it. So K is somewhere in between 10 to the minus 4 and 10 to the minus 5. But we're really not quite sure where. So what we'll do is, let's just try plotting this up. So let's make a plot. It has K here and the residual here, the total residual. So for K of 10 to the minus 4, we have a residual of 18.7. For K of 10 to the minus 5, we have a residual of minus 187. So let's just make a plot of that. And let's, so you need to go in here, it does it by rows, you need to go and make it into columns, or it'll give you a plot that's kind of messed up. There you go. Okay, so here's our residual, the big negative one, the positive one, and here is K. All right, so what we want to do now is use this to estimate, or to improve our guess. So we pretty much have bracketed it. Basically, we want a zero residual. So maybe it'll just be linear between these two. Probably not, but maybe. And so we might just want to guess 10 to the minus, or 9 times 10 to the minus 5. I think it might be good if we guessed a little bit less than that. Let's try 8 e to the minus 5. Well, let's just do this. Let's just say, okay, we'll just do linear interpolation between these points, and we'll pick that. So let's try 9 e to the minus 5. Okay, so we'll just go back here to k. Right click, the attribute table, and we'll try, instead of 1 e to the minus 5, we'll try 9. And then we can map that to my flow and rerun it. Let's take a look at our observation wells now. Okay, so this looks better. So paste these guys. So this was 9 e to the minus 5. Okay. And so now we have a value of 16 for the residual. Well, it's better than 18. So we're getting better, but really probably are going to want to be able to do better than that. So let's move this down here and plot this guy. Listen to it. 9 e to the minus 5, and that would be 16.2. Okay, so there's the one value, and these are these two guys. So it looks like the curve is going to be something like this. So let's kind of extrapolate that out, maybe to right there. So let's try 5 e to the minus 5. Okay. So this is really just trial and error. And we're just using this plot to help our guess. So our next estimate should be 5 e to the minus 5. And run it. And the values that we get now are, well, that looks better. We have some positive and some negative. So yeah, this is looking pretty good. These are, look at small green. This is a little bit high. That's a good bit too high. So certainly seem to be on the right track. So let's paste this. And this we said was 5 e to the minus 5. Okay. And then I'm going to sum it. Oh, look at that. Okay, so now we can put this guy in here, 5 e to the minus 5. That's minus 4.1. Okay, so now we've overestimated, and we're going to come back here a bit. And it looks like maybe around 6 e to the minus 5. Let's try that. So we're definitely kind of homing in on this thing. And so that's encouraging. And that's why I'd really recommend that you use this plotting approach and keep track of the results that you've used and see how the results relate to each other. Because if you just start guessing and really don't try to use the pattern that's developing, this can be really pretty frustrating. So let's try this value of 6 times 10 to the minus 5. And here are these values. So that looks pretty good. These are all less than 1. They're all positive. Last one, remember, was a net negative. So this was 6 e to the minus 5. And yeah, so now this one is about 4 too low and 3 too high. So we're definitely zeroing in on this. And let me do this here and make this one 6 e to the minus 5. Alright, well, so this is getting pretty close. I think if we were to go halfway between these two, we would have something that is probably going to be good enough for our purposes here. So we can just try this. So, optimistic about this one. So, yeah, look at that. All of them are green. So, like the look of that. Copy this. We got a couple negatives, a couple positives. All small numbers. Okay, wow, there you go. So that's a pretty small residual there. Okay, so that looks like our value for now. So that's the value of k that gives us the best match. And it's really pretty close. We've got a couple, all of them except, well, it looks like all of them are within a meter. A few of them are too high, a few of them are too low. So that's pretty good. So that is our estimate for k. Now what I want you to do, that's the first part of the homework. What I want you to do is to repeat this by going back to the baseline where we have the recharge of 10 to the minus 8 and k of 10 to the minus 4. And what I want you to do is fix the k at 10 to the minus 4 and try adjusting recharge. And what you'll find is that, and set it up the same way. Set up a table like this and keep track of the residual as a function of the recharge. And what you'll find is that you can adjust the recharge and you should be able to get a fit that has a small residual like that for the value of k, the benchmark value of k, that is 10 to the minus 4. And the recharge value will be something other than the recharge that we have now. Okay? So go through that exercise, give that a try. I don't want to go through it here because it's pretty much the same operations that we've just done, but you're adjusting recharge instead. What this does is it shows that you can calibrate a model using the hydraulic heads by either adjusting the conductivity or adjusting the recharge. And if you fix one and adjust the other one, you can match the heads equally well. So this is a problem because it means that there's no unique calibration for your model if you just have hydraulic heads. And So that's something that's a very important aspect of model calibration, and it's really the underlying thing that I want you to see by doing the first two problems, or first two parts of this homework. Okay, so it ends up presenting a problem because we can't come up with unique calibration of the model. And so the way we get around that is we use some additional information. And remember when we were looking at the PowerPoint here, we had a couple of different types of information. We had these heads that we've been using, but we also have this, the base flow. And in general, what you need to calibrate a model unambiguously is both hydraulic head data and some kind of flow data, either values of recharge that are determined somehow, or this values of base flow, some kind of measurement of flow or water flux. We'll do it using this value of base flow measured here at this point. So we want to include that in our calibration. And here's how to go about doing it. We'll go back to the stream coverage, and we'll right click on coverage setup, and we'll go down here to observe flow. We'll check that. And we'll also want to go in here to create point, put a point right there. And what that's going to allow us to do is calculate the flow for each one of the reaches. So if we go and rerun this, what we see now is if we go and click this so I can select an arc. When we select that arc, now it's selected right up to that point. That's the reach that we're interested in. And if we go down here, what we see is the computed flow out of this reach is minus 0.105 and change. So what that means is that 0.1 cubic meters per second are leaving the aquifer because it's negative and discharging to the stream. Okay, so this is the total, the cumulative base flow through this reach of the stream. And this is the average base flow because this is a steady state model, so this would be the average base flow. Okay, so now we can use our model to estimate both the base flow to the stream and the hydraulic heads. Okay, and so that will be how we calibrate the model. And the strategy will be to go through the exercise that we just did, where we went and we fit the heads for a particular recharge. So this model matches the heads, but we see that the computed flow here at the stream is 0.1, and actually the flow is 0.072. So our computed flow is too large. We have too much water leaving the aquifer, too much water flowing in the stream. And so what that means is the recharge is too high. And so we'll need to reduce the recharge. And when we do that, the calibration for our heads will be messed up. So but we know how to fix that. Okay, we go and we redo that exercise where we adjust K to match the heads. And then we see what the recharge is at that point. And we either close enough, or if we think we can do better, then we adjust the value of recharge based on the flow, and then redo all of the, and then adjust the K in order to match the heads. Okay? So that then is the strategy for the third part of the problem, where you're going to adjust the recharge and then adjust the recharge to calculate, or adjust the recharge to match the base flow and adjust the K to match the hydraulic heads. And like we did here with this example, we kept track of the K. What you would do is for this value of recharge, you keep track of the K. You come up with a K that best fits for this recharge. And then you'll calculate the flow and see how well you're doing. And then you'll repeat for another value of recharge. You'll have another little grid here and come up with a K that, basically a K and R that best match the heads and hopefully matches the discharge. And what I would do is be plotting the recharge and the base flow and create another plot like this one for recharge and base flow and use that to help guide your estimates of the recharge that you set up in order to match the base flow that you see. And that'll be the procedure. So hopefully if you plot the data up as you go, it gives you some structure so you're not just flailing around and trying many different combinations. This is the manual procedure for calibrating groundwater models, and you should be able to calibrate this one with, you see it took us maybe 6 tries here. Well, we started one and then we had 5 tries, and maybe one of these was really close enough. So 5 or 6 tries to get our value of K, and then if we do something similar where we iterate and adjust values of R, we should be able to do this 3 or 4 times and come up with a calibrated model. Okay, so give that a try and see if you can estimate values of R and K that best fit the data. There are some automated techniques that do this kind of adjustment that we're doing manually here. They do it numerically, and they can be a help with calibration, and so we'll learn about those soon. But it's going to be important to go through this exercise manually and see how it works manually. Sometimes the manual or the automatic techniques aren't available, and actually sometimes they don't really work all that well, and you need to go and do it by hand anyway. So it'll be important to understand how the model calibration process works, where you have these 2 different parameters that are interacting.